Chi-square test. 10. The chi-square test is an important test amongst the several tests of significance developed by statisticians. Chi-square, symbolically written as 2, pronounced as chi-square, is a statistical measure used in the context of sampling analysis for comparing a variance to a theoretical variance. As a non-parametric asterisk test, it can be used to determine if categorical data shows dependency or the two classifications are independent. It can also be used to make comparisons between theoretical populations and actual data when categories are used. 1. Thus, the chi-square test is applicable in large number of problems. The test is, in fact, a technique through the use of which it is possible for all researchers to I. Test the goodness of fit, 2. Test the significance of association between two attributes, and 3. Test the homogeneity or the significance of population variance. Chi-square as a test for comparing variance. The chi-square value is often used to judge the significance of population variance, i.e., we can use the test to judge if a random sample has been drawn from a normal population with mean and with a specified variance, 2. The test is based on two distribution. Such a distribution we encounter when we deal with collections of values that involve adding up squares. Variances of samples require us to add a collection of squared quantities and thus have distributions that are related to distribution. If we take each one of a collection of sample variances, divided them by the known population variance and multiply these quotients by n1, where n means the number of items in the sample, we shall obtain a distribution. Thus, df would have the same distribution as distribution with n1 degrees of freedom. The two distribution is not symmetrical and all the values are positive. For making use of this distribution, one is required to know the degrees of freedom, since for different degrees of freedom we have different curves. The smaller the number of degrees of freedom, the more skewed is the distribution, which is illustrated in Fig. 10.1. Pause the video. 2. Look at the figure. Table given in the appendix gives selected critical values of 2 for the different degrees of freedom. 2 values are the quantities indicated on the x-axis of the above diagram, and in the table are areas below that value. In brief, when we have to use chi-square as a test of population variance, we have to work out the value of 2 to test the null hypothesis, with h0 smiling smiley as under. Chi-square equals 2, where 2 is equal to variance of the sample. 2 is equal to variance of the population, and 1 is equal to degrees of freedom, n being the number of items in the sample. Then by comparing the calculated value with the table value of 2 for n1 degrees of freedom at a given level of significance, we may either accept or reject the null hypothesis. If the calculated value of 2i less than the table value, the null hypothesis is accepted, but if the calculated value is equal or greater than the table value, the hypothesis is rejected. All this can be made clear by an example. Chi-square as a non-parametric test. Chi-square is an important non-parametric test, and as such no rigid assumptions are necessary in respect of the type of population. We require only the degrees of freedom, implicitly of course the size of the sample, for using this test. As a non-parametric test, chi-square can be used, I as a test of goodness of fit and 2 as a test of independence. As a test of goodness of fit, to test enables us to see how well does the assumed theoretical distribution such as binomial distribution, Poisson distribution or normal distribution, fit to the observed data. When some theoretical distribution is fitted to the given data, we are always interested in knowing as to how well this distribution fits with the observed data. The chi-square test can give answer to this. If the calculated value of 2i less than the table value at a certain level of significance, the fit is considered to be a good one, which means that the divergence between the observed and expected frequencies is attributable to fluctuations of sampling. But if the calculated value of 2 is greater than its table value, the fit is not considered to be a good one. As a test of independence, to test enables us to explain whether or not two attributes are associated. For instance, we may be interested in knowing whether a new medicine is effective in controlling fever or not. To test will help us in deciding this issue. In such a situation, we proceed with the null hypothesis that the two attributes, viz., new medicine and control of fever, are independent, which means that new medicine is not effective in controlling fever. On this basis, we first calculate the expected frequencies and then work out the value of 2. If the calculated value of 2 is less than the table value at a certain level of significance for given degrees of freedom, we conclude that null hypothesis stands, which means that the two attributes are independent or not associated, i.e., the new medicine is not effective in controlling the fever. But if the calculated value of 2 is greater than its table value, our inference then would be that null hypothesis does not hold good, which means the two attributes are associated, and the association is not because of some chance factor but it exists in reality, i.e., the new medicine is effective in controlling the fever and as such may be prescribed. It may, however, be stated here that 2 is not a measure of the degree of relationship or the form of relationship between two attributes, but is simply a technique of judging the significance of such association or relationship between two attributes. In order that we may apply the chi-square test either as a test of goodness of fit or as a test to judge the significance of association between attributes, it is necessary that the observed as well as theoretical or expected frequencies must be grouped in the same way and the theoretical distribution must be adjusted to give the same total frequency as we find in case of observed distribution. 2 is then calculated as follows. Chi-square is equal to, where OH is equal to observed frequency of the cell in ith row and JTH column. Age is equal to expected frequency of the cell in ith row and JTH column. If two distributions, observed and theoretical, are exactly alike, 2 is equal to 0, but generally due to sampling errors, 2 is not equal to 0 and as such we must know the sampling distribution of 2. So that we may find the probability of an observed to being given by a random sample from the hypothetical universe. Instead of working out the probabilities, we can use ready table which gives probabilities for given values of 2. Whether or not a calculated value of 2 is significant can be ascertained by looking at the tabulated values of 2 for given degrees of freedom at a certain level of significance. If the calculated value of 2 is equal to or exceeds the table value, the difference between the observed and expected frequencies is taken as significant, but if the table value is more than the calculated value of 2, then the difference is considered as insignificant, i.e., considered to have arisen as a result of chance and as such can be ignored. As already stated, degrees of freedom * play an important part in using the chi-square distribution and the test based on it. One must correctly determine the degrees of freedom. if there are 10 frequency classes and there is one independent constraint, then there are 10 to 1 is equal to 9 degrees of freedom. Thus, if n is the number of groups and one constraint is placed by making the totals of observed and expected frequencies equal, the DF would be equal to n1. In the case of a contingency table, i.e., a table with 2 columns and 2 rows, or a table with 2 columns and more than 2 rows, or a table with 2 rows but more than 2 columns, or a table with more than 2 rows and more than 2 columns, the DF is worked out as follows. DF is equal to C1 R1, where C means the number of columns and R means the number of rows. Conditions for the application of to test. The following conditions should be satisfied before to test can be applied. I. Observations recorded and used are collected on a random basis. 2. All the ions in the sample must be independent. 3. No group should contain very few items, say less than 10. In case where the frequencies are less than 10, regrouping is done by combining the frequencies of adjoining groups so that the new frequencies become greater than 10. Some statisticians take this number as 5, but 10 is regarded as better by most of the statisticians. 4. The overall number of items must also be reasonably large. It should normally be at least 50, howsoever small the number of groups may be. The constraints must be linear. Constraints which involve linear equations in the cell frequencies of a contingency table, i.e., equations containing no squares or higher powers of the frequencies, are known as linear constraints. Steps involved in applying chi-square test. The various steps involved are as follows. First of all, calculate the expected frequencies on the basis of given hypothesis or on the basis of null hypothesis. Usually in case of a 2 times 2 or any contingency table, the expected frequency for any given cell is worked out as under. Expected frequency of any cell is equal to 2. Obtain the difference between observed and expected frequencies and find out the squares of such differences, i.e., calculate 2. 3. Divide the quantity to obtained as stated above by the corresponding expected frequency to get 2, and this should be done for all the cell frequencies or the group frequencies. 4. Find the summation of 2 values, or what we call 2. This is the required 2 value. The 2 value obtained as such should be compared with relevant table value of 2 and then inference be drawn as stated above. Alternative formula. There is an alternative method of calculating the value of 2 in the case of a 2 times 2 table. If we write the cell frequencies and marginal totals in case of a 2 times 2 table thus, then the formula for calculating the value of 2 will be stated as follows. Chi-square is equal to, where n means the total frequency, AD means the larger cross product, BC means the smaller cross product, and A plus C, B plus D, A plus B, and C plus D are the marginal totals. The alternative formula is rarely used in finding out the value of chi-square as it is not applicable uniformly in all cases but can be used only in a 2 times 2 contingency table. Yates correction. F. Yates has suggested a correction for continuity into value calculated in connection with a 2 times 2 table, particularly when cell frequencies are small, since no cell frequency should be less than 5 in any case, through 10 is better as stated earlier, and 2 is just on the significance level. The correction suggested by Yates is popularly known as Yates correction. It involves reduction of the deviation of observed from expected frequencies, which of course reduces the value of 2. The rule for correction is to adjust the observed frequency in each cell of A 2 times 2 table in such a way as to reduce the deviation of the observed from the expected frequency for that cell by 0.5, but this adjustment is made in all the cells without disturbing the marginal totals. The formula for finding the value of 2 after applying Yates correction can be stated thus. In case we use the usual formula for calculating the value of chi-square, then Yates correction can be applied as under. Chi-square corrected is equal to. It may again be emphasized that Yates correction is made only in case of 2 times 2 table and that too when cell frequencies are small. Conversion of chi-square into phi coefficient. Since 2 does not by itself provide an estimate of the magnitude of association between two attributes, any obtained 2 value may be converted into phi coefficient, symbolized as for the purpose. In other words, chi-square tells us about the significance of a relation between variables. It provides no answer regarding the magnitude of the relation. This can be achieved by computing the phi coefficient, which is a non-parametric measure of coefficient of correlation, as under 2n. Conversion of chi-square into coefficient of contingency, C. Chi-square value may also be converted into coefficient of contingency, especially in case of a contingency table of higher order than 2 times 2 table to study the magnitude of the relation or the degree of association between two attributes, as shown below. While finding out the value of C, we proceed on the assumption of null hypothesis that the two attributes are independent and exhibit no association. Coefficient of contingency is also known as coefficient of mean square contingency. This measure also comes under the category of non-parametric measure of relationship. Important characteristics of two test. This test, as a non-parametric test, is based on frequencies and not on the parameters like mean and standard deviation. 2. The test is used for testing the hypothesis and is not useful for estimation. 3. This test possesses the additive property as has already been explained. 4. This test can also be applied to a complex contingency table with several classes and as such is a very useful test in research work. This test is an important non-parametric test as no rigid assumptions are necessary in regard to the type of population, no need of parameter values and relatively less mathematical details are involved. Caution in using to test. The chi-square test is no doubt a most frequently used test, but its correct application is equally an uphill task. It should be borne in mind that the test is to be applied only when the individual observations of sample are independent, which means that the occurrence of one individual observation, event, has no effect upon the occurrence of any other observation, event, in the sample under consideration. Small theoretical frequencies, if these occur in certain groups, should be dealt with under special care. The other possible reasons concerning the improper application or misuse of this test can be neglect of frequencies of non-occurrence, 2. Failure to equalize the sum of observed and the sum of the expected frequencies, 3. Wrong determination of the degrees of freedom, 4. Wrong computations, and the like. The researcher, while applying this test, must remain careful about all these things and must thoroughly understand the rationale of his important test before using it and drawing inferences in respect of his hypothesis.